Okay, so what I want to do today is kind of take a look at some of the concepts behind the decorrelating detector and possibly even the minimum mean squared error detector. Okay, so so before I do that, let me take a step back and say that these two techniques, the linear techniques that we have studied, the decorrelating detector, which is the least square solution to the detection problem, and the MMSE, they are extremely powerful techniques, and they find application in many different problems. And actually, what happens and what has happened with me several times is that a new problem comes to your desk. You are asked to solve the problem as an engineer, and the problem does not conform to the standard ways in which we are used to seeing the problems that we would have solved, for example, during our undergraduate or postgraduate studies. And it turns out that some of these problems, if not many of these problems, can be cast into this linear algebraic framework. And once we do that, then the possibility of applying the least squares and the MMSE techniques suddenly opens up. So maybe not today, but maybe before the end of the semester, I will present to you few of such problems. At first, they appear to have no resemblance to applying the least squares technique, but then they actually do get solved very efficiently, and actually, more importantly, in a very optimal manner by the least squares and the MMSE techniques. Okay, so one example that maybe I will give you now itself is the example of averaging the results that you get by surveys. The civil engineers go out in the field and they conduct surveys of the landscape and the surrounding, etc. And based on the survey readings, the terrain map gets developed, meaning what part of the landscape is at what height, what altitude. If it is some mountainous region, then what is the height of a particular region above, for example, the sea level. Now, the surveyor goes to multiple places, and then the surveyor tries to measure the height of that particular area from different viewpoints. Now, think about how to average the measurements that you get of a particular location. Let us say that it's a mountainous region, and the surveyor is trying to measure what are the heights of different regions of this mountainous locality. And so he makes one measurement, but he knows that that measurement may not be accurate. So he goes to some different location and again does the survey. So basically, he gets multiple measurements of what is known as the altitude above this mean sea level, or ASML, altitude above mean sea level. So you see that as a part of this measurement, the surveyor will get multiple measurements for any particular location in this landscape, in this region. But those measurements may not be directly one-to-one, because one measurement may be obtained when the surveyor was at the foothill of the mountain. The other measurement might have been obtained when the surveyor was maybe at a little bit of a height. Maybe there was a small hill or somewhere, something like that. And so, yes, you have measurements of the height above the mean sea level of this entire locality, but those measurements cannot be put in one-to-one correspondence. Plus, individual measurements themselves may be having instrumental errors, measurement errors, and so on. So you do get multiple sets of measurements, but then how to combine them becomes the statement of the problem. Now you see the way I have described this problem, it has nothing to do with electrical engineering or communication systems or signal processing, nothing. This is purely a civil engineering problem. And I have seen in my personal experience that this problem would come to the desk of an engineer, and that engineer is actually, and not only one engineer, it's a team of engineers, and everybody in that team are highly qualified, very clever, very resourceful people. And they all came up with some way of solving the problem that I described. And none of those solutions were working out very well. In that there would remain a lot of errors in the final survey data. That is a combination of these multiple measurements. And then the entire problem went to some other company, and that some engineers in that other company figured out that this problem actually can be cast in a manner where the least squares technique can be applied. And the least squares technique gives the optimal performance. So the whole data set, this huge, humongous data set that the surveyors had collected, was processed using a technique which was exactly like the decorrelating detector that we have seen, except the matrices themselves were obviously different. And the equivalent of the decorrelating detector or the least squares method produced a result which was highly accurate, much more accurate than the use of some ad hoc techniques that the engineering team in this other engineering company had used. So the point that I want to drive home is that this mathematical topics of least squares and MMSE that we have studied, although we have studied them in the context of communication related problems, signal processing problems, it may so happen that some problem which has not much connection to the communication engineering, and it doesn't seem initially like it would have anything to do with the decorrelating detector, ends up actually being in a form where the same decorrelating solution can be applied. So given the widespread applicability of these two linear techniques that we have studied, I thought that maybe we should spend a little bit of time in understanding the mathematical underpinnings of these methods. The way we have so far formulated decorrelating detector is by just writing equations. We have said that if our received vector can be written as some matrix multiplied by the vector of unknown, then well, I can form a sufficient statistics vector by taking the matrix product with the received vector R, and that sufficient statistics vector can be written then as a square matrix of correlation coefficients, which can be inverted. And once we invert that, we get the decorrelating solution available to us. Now, in all of that, we have not justified why that solution is going to be optimal. And that is the purpose of my slides today. I want to show that the decorrelating detector and in general the least squares technique actually achieve the optimal solution. They provide performance which is superior to the alternative techniques in some very specific quantitative manner. So with that as the kind of preamble, let me begin. And here I'm going to consider a very simple model, which is the equation of a line, which we all are familiar with. Y is equal to mx plus c. And the way we can draw this line is as a collection of 2 cross 1 vectorial locations. So these are just the coordinates of the points on the line, x and y. And for some technical reason, I would like the line to pass through the origin. And so I removed the constant c from the y coordinate. I don't have to do that. I can keep c outside of this. But let us, for the sake of simplicity, consider this to be the case. Now, once we write the line in the coordinates of line in this manner, we can write it also as the function of the slope parameter m and the variable s. So x coordinate is going to be 1, y coordinate is going to be m, and s, you can think of it as a slider. As you make s go from 0 to some high positive value, we are sliding the point along the line. And now I'm going to call this vector 1m, where m is the slope, as this vector h. Okay, so that is what I have drawn over here. This is the line that is passing through some constant y equal to c. And the locations on this line, the points on this line, fall along this directional vector, which is the column vector h. Okay, so this is the way to look at the geometrical realization of the equation of the line. Okay, now in generality, what I would like you to think of this h as not necessarily just a vector, a 2 cross 1 vector, but it can be some n cross k matrix. Once we consider h as an n cross k matrix, we are back to the problem statement that we have formulated earlier, either in the case of beamforming, MIMO, CDMA reception, etc. Now, when we consider H not as this 2 cross 1 vector representing a line, but as a matrix, n cross k matrix, then you might ask that how can I represent that matrix as this line, the line that is shown here? Well, in that general case, this particular line here represents the column space of that matrix capital H. Okay, so this is now an abstraction that I would like you to consider. Remember that matrix H, that the one that we have seen earlier. Let me go to this unified signal model. This is that matrix H that I'm talking about. This is the n cross k matrix. K is the number of simultaneous transmitters, and n is the number of measurements that we obtain. Okay, so this is that matrix capital H. In the diagram of a line, this S is just a scalar. It's a scalar that allows us to slide the point along the line up and down. In the general formulation, S becomes a vector instead of a scalar. And then R is the measurement that we get after this linear model gets corrupted by some additive noise. So this is the equation that I would like you to consider. I would like you to visualize by this equation of a line. I cannot draw this n-dimensional space in which I can put a k-dimensional subspace. If I can do that, then it will be an accurate depiction of that equation that I had just projected on the screen. And so, for the sake of visualization simplicity, I'm considering, instead of a matrix H, I'm considering a vector H. And instead of a vectorized model of this unknown variable S, I'm considering this S to be a scalar. But the generalization applies. This line here becomes the column space of that matrix H, and S is the unknown parameter. For the equation of a line, S allows us to move up and down this line, as I mentioned earlier. Now,
sir.
Yes.
Sir, can we say that this diagram represents one of those K simultaneous transmitters?
Can this diagram represent one of the K simultaneous transmitters? Probably not, right? I mean, this is a very simple model. It is a 2x1 vector H.
So you said that H belongs to the column space of H. So I was thinking.
No, I'm saying that this line that I have drawn here, you want to think of it as column space of capital H matrix, that n cross k matrix. Meaning, if you take all possible linear combinations of the columns of matrix H,
okay,
you will form a k-dimensional subspace of the n-dimensional space. And so that you want to visualize it as this line. Okay, so this is kind of a two-dimensional simplified version of that general equation that I had shown to you earlier. In this case, capital N is just 2, right? I'm just considering 2x1 vector. So capital N is 2. Capital K is just 1. I have only one scalar here. But the reason I have simplified it like this is because I can draw this type of diagram. Now, the actual received measurement is not just H times S. It will have some noise present. And that noise is going to be arbitrary. And that noise will make the received measurement be off from the line. Right? If there was no noise, then the measurements are going to be confined to this column space of matrix H. But in the presence of noise, the received vector will necessarily move away from the column space. That is what the noise does. So I'm going to draw a received data point. Again, it's a two-dimensional point. And I'm going to make it some point in this two-dimensional space which is not located on the line. So I'm calling it some point R. It has coordinates of xp and yp. And it is not on this line. Now, Our problem is to figure out what is the best possible estimate of this S, the unknown parameter, given that I know the model H and I get some measurement vector R. So from this, I want to figure out what is the best possible value of S that I should use. I want to form an estimate S hat of S. Now, obviously, I should form that estimate S hat for which the corresponding R hat, which is H times S hat, comes closest to the actual measured data point, right? Because that I want to be best able to explain the measurement that I got using the estimated S hat. And the way to do that is to make sure that R hat corresponding to S hat is closest to R, because that is where I will have kind of done the minimum Euclidean distance detection. And remember, minimum Euclidean distance detection is always preferred. If we go to probabilistic method, then that is the answer we get by applying maximum likelihood technique. So we want that value of S hat as our best estimate, for which the corresponding R hat comes closest to the actual R. Now, R hat is necessarily going to be confined to this line, because R hat will be H times S hat. And remember, the way I have formulated this diagram is such that S is a slider. It's a scalar which allows me to slide the location of the point along the line anywhere I want. Which means that I want to choose that value of S hat for which the point comes closest to R. And the way it will come closest to R is when the corresponding H times S hat, this location shown in the green over here, the line connecting the green point to the red point is perpendicular to the direction of the line, right? If the green point were to move anywhere away from the location that I have shown, meaning that this angle, instead of being 90 degrees, if it becomes any other angle, then obviously this vector that I am calling vector E will become longer in length. Only when this is a right angle triangle, then the length of E is going to be the smallest. Does it make sense?
Yes, sir.
Yeah, I wish I had yeah, maybe I think it should be fairly clear to you, but just for the sake of it, let me kind of do some type of visualization. Okay, so I'm going to draw a line here. This is that column space vector. Okay, this is that same vector that I was vector H that I had drawn, and I'm going to put up some vector R, which is my measurement vector R. And now I'm going to pick up another one, another vector. And this point that I'm moving is I'm able to slide the let me just put another one here. This is that green colored point that I had shown. Okay. So you see that by changing the value of S, basically that unknown estimate S hat that I'm considering as the parameter that allows me to slide up and down this line. I want to make that S hat for which this red colored line becomes the smallest in length. And you see that it became smallest in length when the red and the black are perpendicular to each other. As soon as they become not perpendicular, the length of that red line increases. It gets minimized when they are perpendicular. So that is the point that I was making here, that I would like the estimated R hat, which is H times S hat, to be as close to R as possible, because that gives me minimum Euclidean distance estimate. And that happens only when this vector E, which is the one that I have shown here by this red colored line, becomes perpendicular to this column space H. Okay. So now let us cast this in a little bit mathematical terminology. Yes, Divya?
So is it related to the projection matrix concept?
Yes, absolutely. Essentially, the other way to say what I'm saying, which is what Divya has pointed, is that we would like to project R onto the column space of H. So ultimately, we are going to derive the formulation of projection matrix. But let us state the objective of what we are doing in a linear algebraic manner. Basically, we want R hat to be along the vector H, and we want it to be perpendicular to the vector E. Now, this is what I was saying, that if I want to use some fancy linear algebraic statement, then I would say that vector E should be in the null space of H transpose. Okay. So this is H, and you may know that the null space of H transpose is perpendicular to H. H is, in general case, it is this n cross k matrix. So this will be the column space of H, and the null space of H transpose, not the null space of H. The null space of H transpose is the it's called the orthonormal complement of the column space of H. And so if we use formal linear algebraic statement, we would say that vector E should be in the null space of H transpose, which is a way to say that E is perpendicular to H. In this case, the direction which is perpendicular to H is minus M1, because if I take the dot product of E with H, it will become 0. Minus M times 1 plus 1 times M, which is 0. So the dot product has to be 0. Why do you think the dot product is 0 when E is in the null space of H?
So the terms in the null space are
But I didn't get you. Your voice is not very clear.
hello.
Yes.
Is it clear? Hello.
Yeah.
So I said the null space will have terms which are very less, so it is directly ortho. I mean they are 0, so any of the put into the which
No, null space will have elements which will not be small. Null space will be formed of vectors. Actually, the null space will have its own basis vectors, and they will have their own, they will have unit length and some arbitrary directions. But the question that I was asking is why is it that if vector E is in the null space of H transpose or H Hermitian transpose, H Hermitian transpose times E becomes 0. That is the definition of the null space of H Hermitian transpose. All the vectors in the null space, if you take H Hermitian transpose times that particular vector, you will always get 0. That is how the null space is defined. My question is, in this case, why that is the case? See here, remember that H...
Sir, geometrically, the angle between them is 90 degree. So when we take dot product, the cosine of that angle becomes 0.
Exactly, right. So H Hermitian transpose E is nothing but a dot vectorial dot product, which is defined by the cosine of the angle, as Joel is saying, and that angle is 90 degree. And therefore, this becomes 0. Right? Now, if you read some textbooks or some tutorials on a lot of this machine learning methodologies and signal processing schemes, adaptive algorithms, etc., you will come across a notation which is called orthonormality condition, or orthogonality condition rather than orthogonality condition. And it will be described in many different ways. But this is a visual way of stating the orthogonality condition. The orthogonality condition says that the error vector should be perpendicular to the column space, so that this dot product turns out to be 0, which is to say that the error vector is in the null space of the model matrix H. Okay, so now all that, okay, I won't go into this. Maybe you can read it on your own. But now all that we need to do is to plug the formulation for E, the vector E, in this equation. Remember, vector E is the difference vector, r minus r hat. R is the actual measurement, r hat is the constrained modal vector. It is constrained to lie on the column space of H. And therefore, r hat I can write it as H times S hat. So the error vector becomes r minus H times S hat. And this is the defining equation in which all the terms are known except S hat. And so it is now just a matter of expanding the equation. H hat times R minus H hat times H times S hat, that has to be 0. And so now I can solve for this equation here on the second line, and it will give me the final solution, which is given as this last equation. And this is known as the least squares solution. Now, you may recall that this H Hermitian R is what we have been calling the sufficient statistics vector. And we have sometimes denoted it as vector Y. And this H Hermitian H, what would you call that?
Capital R.
It is our correlation matrix R. And remember, our estimate is R inverse times the sufficient statistic vector, which is exactly this last line. Let me just momentarily go back to this equation here. We have been kind of juggling the notations a lot, but in this equation 4, this vector Y is equivalent to that vector R. W should be H. W Hermitian X is the one term of that least square solution. That allows us to get, X is our measurement vector R. This is our measurement vector R, and W is equivalent to matrix H, and S is the unknown parameter of vectorial parameter of interest. And so in this equation we take W Hermitian X, which is equivalent to this part of the equation. W Hermitian X is this this part of the least square solution. And then once we do that, in the next step, we did R inverse Y. And that R inverse is captured over here by this H Hermitian H inverse. Okay, so the decorrelating solution that we had looked at, we can arrive at that solution, but now we have arrived at that solution by solving some objective function. We wanted to minimize the Euclidean distance between our estimate and the observation. So that way we can say that our decorrelating detector is mathematically motivated. There is a reason why we are doing this specific set of operations that we do to arrive at the decorrelating solution. Divya mentioned that this problem can be considered as a projection operation. And so this doesn't give us the projection of R onto the column space of H. This doesn't give us that. This gives us the solution vector as hat. But if we want to project R on the column space of H, effectively we would derive this vector R hat. Because remember, R hat is the one which is corresponding to this green dot. R hat is the projection of R onto this column space of matrix H. We already have determined the formulation of S hat. And so now, over here, if I multiply S hat by H, then I get R hat, which is the projection of R onto the column space of H. Okay. So let me use the power. Okay, so I'll say that estimate of S is H permission transpose H inverse times H permission transpose. This is the estimate, the least squares estimate of H, this equation over here, times R. And so the projection of R onto the column space H is essentially the same equation, except I have to multiply it by H. Let's see. Okay, so this is the projection of R onto the column space of H. This I can write it as some projection matrix P times R, where P is the projection matrix given as this. Okay, so this is where we can obtain the projection matrix corresponding to this matrix H. Remember, this H we have here taken it as a vector, but in general it is a matrix. Now, suppose H is indeed a vector, and secondly, let us say that H is a unit length vector. So I will write it down here. When H is a unit length vector, what will be the equation for P?
H into H Hermitian.
Correct. H into H Hermitian, because this dot product becomes 1 because H is defined to be unit length. So it becomes H into H Hermitian. So for the specific case when H is a unit length vector, projection matrix takes this form over here. Now this you may recognize was one of the problems in the exam. I told you instead of H, maybe I use some different notation, but I had asked you that if there's some vector whose length is unity, and if I form H times H Hermitian, then the matrix that I get is a projection matrix. That is the one that I had asked you to show in the exam. And so I saw the solutions that some of you have turned in, and you have taken a mathematical approach to prove that. But here we are kind of taking more of a visual approach to show why H times H Hermitian H inverse times H Hermitian gives you the projection matrix. It gives you the projection matrix because with that operation we are projecting R onto the column space of H, where that projection is done in a perpendicular manner. If H is not a unit length matrix, then also we can say that the answer is still H times H Hermitian, except there will be some normalizing factor, some constant corresponding to inverse of H Hermitian H. So as long as H is a vector, if you take H times H Hermitian, the matrix that you get is a projection matrix onto the column space of onto the direction of H. In general case, when H is a matrix, then you can't bring H and H Hermitian next to each other like what I have done here, because there will be this inverse of the correlation matrix that will be present, and you can't factor it out. So in the general case, when H is a matrix, this is the full form of the projection matrix. Okay, so fine. Now let me continue. So this was sort of the visual or geometric or maybe linear algebraic viewpoint. And using that viewpoint, we have derived this solution, the least square solution. Now let me take a different approach and derive this same solution using calculus techniques. So what I'm going to say now is that I have some measurements R, which are some parameter S times this model parameter H. And I have a bunch of such measurements. So I have, let's say, a total of capital N such measurements. And my goal is now to find the best value of S that explains this measurement. Now here, unlike what we did previously, where I had to bring the, if you recall, I had to bring the constant C on and subtract y as subtract C from y. In this calculus-based derivation, I'm going to not do that. I'm going to look at this equation here and interpret this itself as equation of a line. H is corresponding to my X coordinate and R is Y coordinate, and S is the slope parameter. S is now not the slider. It is actually the slope. And different values of J will give me different locations on the line. So Rj is equal to S times H of J. And the effect of noise is going to be that my actual observations will not fall exactly on the line, but they will kind of go up and down. So let me just show you a picture. So look at these two pictures on the left-hand side. This is one picture where these blue dots are R of J, and I have made noise to be pretty small. It's a low noise measurement case. And so you can see that different values of R of J, a total of 25 data points, they together form almost a straight line. If I increase the noise, then they are not always on the straight line, but I can still pass a straight line through these data points. And now my goal is to come up with this straight line, which is given as S times H, where H is, remember, the X coordinate, R is the Y coordinate. So I am given all of these X coordinates corresponding to all the blue points. I know the X coordinate. My goal is to come up with the slope parameter S, so that S times that X coordinate, which is H, gives me this measurement, the modeled versions of the measurement, such that the line that is formed is the best fit line. And so now I'm going to define this cost function, R of J minus S times H of J whole squared. This is known as the sum of the squared errors. R of J minus the best fit location on the line will give me the error values. So these are the individual errors. I'm going to square all of these errors, as you see here, and then I'm going to take a sum of all the squared errors. So this is known as sum of squared errors, or SSE. There is an alternate version which multiplies this L of S hat with 1 over. And then the corresponding equation becomes mean squared error, or MSE. So MSE is sometimes more frequently used, but that 1 over n multiplier doesn't change the statement of the problem. So either one is fine. So then the question becomes, how do I minimize this cost function, the MSE function or the SSE function? Well, one way to do that, because you see, I already have the H values. These are the model vector elements. I know them. I also have the R values. These are the actual observations. These are the blue dots in my chart. I can just change S from some small value to some high value. And for each value of S, I can compute this mean squared error, the cost function. And then I will just plot that cost function and see how it looks like. So here, the actual value of S that I used to generate these blue dots was 5. And after generating these blue dots, the observations are, I plug them in this equation. But I said that now I will pretend that I don't know S, and I will change S from some small value such as 2 to some high value such as 8. And for each value of S, I computed the mean squared error that was shown on the previous slide. And so this is how the mean squared error looks like. This is the cost function. Obviously, it becomes 0 when S is actually 5, because that is when this red line is going to pass nicely through all the blue dots. When S is 2, the red line will be way off. It will have much lower slope. If S becomes higher than 5, then the red line will have much higher slope. So it will not be the best fit line. And I will just now say that my cost function is minimized at S equal to 5, and so that is my estimate. If I have very noisy measurements, still this method works. Exactly at, or if not exactly, very close to the actual value of S, this parabola gets minimized. Although now the mean squared error is not 0 because there is a lot of noise. If I now consider even higher values of noise, I mean, these blue dots don't appear as if they are anywhere close to the line. Still, I get an estimate of S which is not that far from the actual value of 5. I get something like 4.2 or something. That is where this cost function is minimized. Okay, this doesn't have to be just now this k equal to 1 case. I can have two different elements in the vector S. So this is as if capital K became 2. There are two transmitters, and therefore there are two unknowns. But I can still do the same formulation that I have stated here. I will still get a scalar value for each vector S. So now this cost function will become two-dimensional. And I want to go to the bottom of this two-dimensional bowl. There are some adaptive algorithms which actually slide down this bowl, and with the hope that they will reach the bottom of the bowl. But instead of using those adaptive algorithms, what I can do is I can take the derivative of the cost function with respect to S and just set it to 0. So this is now the calculus-based technique. This is pretty straightforward, your high school math derivation. Once I set this cost function to 0, and then I solve for S, basically I take this equation, set it to 0, and solve for S. I get this equation over here. Solution of this equal to 0 is given as this. But you will recognize that this denominator maybe we'll get to that later. This denominator hj squared is nothing but h Hermitian h inverse. And the numerator is same as the inner product of h with r. This is the inner product of h with r, and this is h Hermitian h inverse. So this equation that I obtained through the calculus method and by defining this cost function is identical to the one that I got previously by the linear algebraic manner. So this is another derivation of the decorrelation detection. It allows us to go to the bottom of the cost function in one shot. It just directly gives us the optimal solution. As I was saying, we don't have to necessarily do the entire least squares operation, because for for vector h, this is not computationally intensive. But if I consider h as a matrix, then the main problem comes in inverting this h Hermitian h, which is going to be this correlation matrix R. It will have size of k cross k, and we'll have to invert this matrix R. And that is where the algorithm may become computationally expensive to implement. Now, in fact, we have seen some computationally efficient methods for implementing this solution. Specifically, we have looked at Cholesky's factorization. And we have, I don't recollect if we went into the singular value decomposition in a lot of detail, but that is another way to implement this same least squares technique, where we don't have to necessarily implement the inverse of this correlation matrix. But there's one more technique, which is this gradient descent technique, which is sometimes used. It's called the adaptive technique or the iterative technique, which arrives at the least square solution in an iterative manner where the matrix inverse is not needed. And then there is a very simple version of this gradient descent, which is called the least mean squared or LMS algorithm, where the computations are even more simplified. And essentially, the idea behind this gradient descent or the LMS is, it's almost like you pick a stone or a marble and you put it in the bowl. And then you want that marble to kind of follow the laws of gravity and descend down to the bottom of the bowl. And the way you are making sure that it follows the laws of gravity is by setting the gradient. Basically, you want to make your iterative updates which are in the negative direction of the gradient of the loss function at any particular point. That is why it is called gradient descent. You are updating your initial estimate of S hat such that the new estimate goes towards the bottom of the bowl in the most direct manner possible. And that happens when it follows the negative of the gradient. And then there is this learning parameter eta, which also is known as the step size. And it allows you to determine how quickly you want to reach to the bottom. And one analogy that is sometimes given is that if you make eta to be large, then yes, the stone or the marble that you would put initially somewhere over here, because your initial estimate of S hat may be inaccurate, it will very quickly slide down to the bottom of the bowl, but then it will oscillate around the bottom. And maybe eventually it will come to the rest at the bottom of the bowl. If eta is too large, then it will never rest. It will never come to a rest. It will just keep on oscillating like this, like how I'm showing through this cursor. On the other hand, if you make eta to be small, then it will go down to the bottom of the bowl by taking very tiny steps. It will gradually slide down to the bottom of the bowl, and then it will come to the rest right away because it is going there in a very slow manner. And so there will not be this oscillations anymore. The marble will not be going up and down around the bottom, but it might take a long time before it settles down. So the number of iterations may be large. And so I have done that in the context of least mean squares algorithm. So in one case, I made noise to be small. The other case, I made noise to be large. The parameter S, the vector S was 3 cross 1. And the algorithm was initialized at some 0 values. And it quickly adapted to the right solution. If I make the step size parameter larger, then the algorithm converges faster, but it may go up and down a little bit more also. And if I make it too large, the step size is too large, then it might just diverge. It may never settle down to the bottom of the bowl. So this is the trade-off involved in the design of this adaptive gradient descent algorithms. How to choose the value of eta so that this convergence happens in a smooth manner. Ideally, you want the convergence to look like this, or maybe even like this. This is not too bad. And so there is a lot of design techniques that have been developed that focus on how to determine the value of the step size. But you want to keep in mind that this technique is ultimately going to give you the same solution that this least squares technique gives you in one shot. And it is not going to outperform the least squares because it is actually trying to get to the least squares solution without doing matrix inverse. So one way to think of these gradient descent techniques is that they are computationally simpler schemes which don't require this matrix inverse which is needed for the least squares. Okay, fine. I think there are two more topics that I want to cover. Maybe I'll take a quick break and then we will look at these two other computational techniques. Okay. Now, I want you to consider this equation over here. Let us suppose that our measurements are the measurement of some constant S, which has some additive noise present. And I want to form the best estimate of S. What I'm saying is that the best estimate, which is the least squares estimate, is given by this equation. So there are two questions for you. One is why this is the least squares estimate. The least squares estimate, as we have seen earlier, it is given as H Hermitian transpose H inverse times H Hermitian transpose R. This doesn't look like that. But I'm saying that it is exactly the same solution. So my first question is why that is the case. Now, I will give you just 1 minute to think about that. If you have a quick answer, I will take it. Otherwise, we'll park that question and then I'll go to the next question.
So
can anybody tell
the question?
Yeah, my question is that this equation that I have written here, which is an estimate of S, where S is a constant. which is measured in some noise, and I have some n measurements. When I have n measurements of S in the presence of noise, then the least squares estimate of S is given by this formula. By the way, let me ask the second question that I was going to ask first, actually. What is this formula? What does this do?
So this calculates the mean.
Exactly. This is the average.
Sir, if we replace h of j as 1 in the previous formula, we'll get this, because like all the h values will be 1.
Correct. So Joel gave me the answer to both the questions. The one question was, what is this? So this is nothing but simple averaging, right? I'm just averaging all the measurements. I'm taking the mean value. Why is the mean value a least squares estimate of this constant? Because again, like Joel said, I can cast this equation in that linear form by taking all of h of j to be 1. So vector h becomes an n cross 1 vector which has all ones. So when I have n cross 1 vector filled with ones, and if I do h Hermitian h, I'm obviously going to get capital N as the answer, because I'm just adding n ones. And so this 1 over n is nothing but h Hermitian h inverse. And then this part here is nothing but the dot product of h with r. So the simple averaging that we do all the time, every time you do this in Excel or anywhere else, what actually you are doing is forming the least squares estimate. So fine. So suppose we are doing this. Let us say we are doing this in Excel, or we are doing it on an FPGA, and now I want to consider a case where a new data point is coming in every few seconds. Maybe the Excel gets updated with a new row. Basically, this n keeps on increasing. First, I have only 2 measurements, then 3, then 4, 5, and so on. And so one way is to do this averaging all over again. Every time I get a new point, I compute the average of all the previous points plus this new point. But then we realize that computationally, maybe that is not the smartest thing to do, because my previous average already contains a lot of the calculations that I need to do to compute the new average after a new measurement arrives. And so let us say that a new measurement arrived. We already have computed the average for the previous case. And I want to now formulate the average after getting this n plus 1th data point measurement. So obviously the average over those n plus 1 points is given by this first line. And so the second line is where the trick comes. I will write the first line as the previous value of average, this equation here, average obtained over the first n data points, multiplied by this multiplier. N plus 1 comes because there is n plus 1 here in the denominator. And this n comes because I want to get rid of the previous value of n that I have divided the average by. So this will just give me the summation of r of j for the first n points. And then I just add the new data point that I got, but now I have to divide it by n plus 1. So the second line is a way to write the first line. Now I can write the second line in this manner, the way I have shown it in the third line. The reason I'm rewriting the second line in this manner is because now I will interpret S hat of n minus 1, my previous value of average, as my best prediction of the new data point, R of n. And this quantity here is the difference between the two. So this, I can think of it as prediction error. And so now the way I'm going to update my estimate in a recursive manner is I will take the previous least squares estimate, I will form the prediction error as it is shown here, and then I will scale the prediction error by 1 over n plus 1. Why is this scaling needed? It's because when n becomes large, then I'm kind of trusting my previous average a lot. I have already averaged the data a lot. And so that average is getting to be pretty accurate. And I don't want to keep on changing that average for each new data point that comes in a very drastic manner. And this denominator n plus 1 actually kind of attenuates the change that I make to my current estimate due to the prediction error. Basically, as n becomes bigger and bigger, I do not care too much about the prediction error. I just pretty much use my previous average. When n is very small, when I'm, for example, starting out, then most of my S hat is controlled by the prediction errors. Because at that small values of n, I know that my average is not accurate. And so I need to chase each and every prediction error that I'm making. Okay. So this is for a simple case where H was a vector of all ones. But the idea then generalizes for an arbitrary case where the equations are given like this. Now this may be vectors actually instead of scalars. But the idea remains the same. We have already obtained an least squares estimate at after n data points. We multiply it by the model vector or model matrix to form an estimate of the next data point. And then I measure the prediction error. That prediction error I multiply with this gain term, k of n. K of n for this example was very simple. It was just 1 over n plus 1. In the general case, k of n takes a complicated form, which is shown over here. And it is driven by this correlation matrix, sigma. And I need to keep on updating the estimate of the correlation matrix also. So this is in general what is known as the recursive least squares. The idea of recursive least squares is also powerful, and it allows us to obtain the least square solution when the data is coming in a sequential manner, in a timed sequential manner. And the reason why this is computationally efficient is because this k and sigma, they are not dependent on R. You see, they are independent of R. They are dependent on H and the measurement variance. But they are available to me even before I start the algorithm, even before I start processing the data. So actually I can compute k and sigma offline ahead of time when I'm not constrained by the computational time that is needed to solve these equations. So I can take as much computation time as I want, and I will calculate this k and sigma values, and I will store them. And then in the real time, in the online mode, I just need to do this operation, the first equation, which is very, very simple. So I can pretty much trade the computational time complexity with the memory complexity or the space complexity. I will have to store all these k and sigma values, but then the number of fixed point or floating point operation per seconds, I don't have to worry too much about that, because that has become much simpler. The same solution I can get by doing the least squares, but that least squares, if I have to keep on doing that matrix inverse every time I get a new data point, you can imagine that then there will be a lot of flops, floating point operation per second, that may become unwieldy, especially as capital N becomes large. Okay, so we looked at the stochastic gradient descent. We looked at the recursive updates, the RLS solution to the least squares. Okay, now maybe the last thing for today is one more variation of the least squares, which is known as, sorry, okay, the last thing that I want to look at is called weighted least squares. And this is also very, very, very important extension of the least squares technique. Sometimes the least squares technique fails, but the weighted least squares technique works very well. So again, I'll first describe the concept and then generalize it. Okay, so let us consider some practical real-world scenario that somebody is trying to measure his or her weight, but the person knows that the weighing scale is pretty flaky. It gives the estimate of the weight, but sometimes that estimate is not very, very good. And so one way is to measure the weight 2 times. You step up on the weighing scale 1 time, look at what the reading is, and then you see, oh, well, maybe I don't trust that reading as much. So you step off and then again step back on and then again measure your weight. In fact, this happens a lot of the times, even at the doctor's office, or if you have a weigh scale at your home, you might have done it when you check your weight. And then obviously we do the average of the two readings. And I have already told you that the average is the least square solution. Here I have just explicitly written it down. What is the cost function? What happens when I set the derivative of the cost function with respect to the unknown to 0? Basically, I get the average of the 2 readings. So this is just the least squares approach. Okay, now suppose we consider a case where these 2 readings are not on the same weigh scale, but 2 different weigh scales, and we know ahead of time that one weigh scale was purchased maybe 20 years back, and it is pretty flaky, and the other weigh scale is more recent and it is well calibrated. So then what to do? Well, one simple solution is to say that I'll just use the weigh scale which is more recent and more accurate, and I'll just throw away the reading that I get through the second weighing machine. basically I won't even use that second weighing machine. But well, the estimation theory says that if you already have the second weighing machine, then you should actually make use of it. Even though you know that it is going to be pretty erroneous, still go and measure your weight there. But then after measuring the weight, don't give it as much importance. Put a higher emphasis on the first reading because it came through a more reliable measurement tool. But still use the second measurement, although it comes from a less accurate device. And the way to do that is to multiply the first reading by a weight W1, second reading by a weight W2, where you would want to make W1 to be larger than W2. Maybe you can make W1 to be 10 and W2 to be 1. Or if you think that second weigh scale is very bad, then you can even make W1 to be 100 and W2 to be 1. But don't make W2 to be 0. And with that, the cost function, the mean squared error function will be defined like this. I will set that with respect to 0, and now I get this as the answer. This is what is known as the weighted averaging. You might be familiar with weighted averaging, but in the context of least squares, this becomes weighted least squares. Essentially, what I'm doing is I have the measurement vector R, and I'm weighting these values of R by different amounts. And those weights are captured in this matrix W. Typically, this W is a diagonal matrix. So for the previous example, it would be a diagonal matrix whose first element will be 10, the other will be 1. And to be consistent, when I multiply R with W, I should multiply the left-hand side also with WA. And so now I have this modified equation. And I then do the least squares on this modified equation. Remember, WA times R is going to be also a vector. And WA times H is also going to be a matrix. So in the standard least squares, which is H Hermitian, H inverse H Hermitian, R, I replace R with WA times R. This one over here. And then wherever I have H, I replace it by WA times H. And so I get finally this equation. And a lot of the times you don't need to have WA separately. You can just compute the product WA Hermitian WA, just call it W matrix. And then finally you get the expression for the weighted least squares. Okay, so that is the enhancement of the least squares technique that is sometimes very, very effective. The question becomes, what should be the W matrix? So a short answer to that is that if you know the signal to noise ratio, for example, then you can set W to be a diagonal matrix of those SNR values. So now if you have, let us say, 2 measurements, and you know that first measurement has a SNR of 10, the other measurement has SNR of 1, then W matrix will be a diagonal matrix with 10 and 1 as a diagonal. In general, it may not be relevant to talk about SNR, but it may still be possible to talk about the covariance of R, meaning what are the what is the covariance matrix of R? And then W would be the inverse of that covariance matrix. And so the elements of R which have a lot of jitter, they will exhibit a lot of, basically the variance will be high, and corresponding to those high variance terms of vector R, we will apply a lower weight because W is the inverse of the covariance matrix. Okay, so I think I will stop here for today. Next time when we meet, I want to go over the concept of the minimum mean squared method. I hope I'll take no more than 15 to 20 minutes to cover the MMSE technique. So that is my plan next time when we meet. And then I want to conclude this entire topic of, remember we have been calling it as generalized modulation and demodulation techniques. I want to conclude it by looking at a technique called sphere decoding. So we will spend some time on understanding what this sphere decoding technique is. In the lab that I have given you, I have not asked you to do any of this recursive least squares or least mean square error, weighted least squares, etc. I have not even asked you to do sphere decoding. So today's lecture and the next lecture, which we will do on MMSE technique and specifically not MMSE, but the sphere decoding, it will be probably we will not have time to do a lab on that. Because there are some other labs which are more important that we will try to squeeze in before the end of the semester. But in case if your research actually requires you to develop some of this adaptive techniques or weighted least squares or maybe even sphere decoding, then maybe after the conclusion of the semester we can take it up as a kind of a self-study project. So today's lecture and maybe even the next lecture, there will not be a counterpart lab to these two lectures. But as a concept, I think today's lecture and the next lecture are kind of useful because they establish the theoretical underpinning of the least squares, the MMSE, and next time when we will study this sphere decoding technique, we will kind of get a broader idea of what are some of the innovative, clever techniques that are currently being leveraged in the research community to solve the same generalized problem that we have been studying for past several weeks now. Okay, so with that, I will conclude today's lecture.